Here we have a short page of notes to look at the energy stored in the electric field. Now this is done through, as it says here, the energy density. Now the energy density is the energy, joules, per meter cubed per volume for the joules of energy within the electric field. So the electric field sits between the plates of the capacitor. So we're going to use our parallel plate capacitor to facilitate our discussion. And we have our positive at the top, negative at the bottom, and the electric field occupies this volume. That's the meters cubed that they're talking about. So the volume that the electric field occupies. Now, a lot of textbooks do use a more scripty U, but it's lowercase u. It's energy per volume. Now we've used U as it says here for the potential energy joules, but this is the joules per volume. A is the cross-sectional area of the plate, so that's our cross-sectional area up here. And D is the distance between the plates, giving us our volume. Now on our previous page of notes, we have the result that the energy for the capacitor, 1/2 CV squared, is correct for all capacitors, regardless of whether it's the parallel plate or not. So we use that for the 1/2 CV squared. And as we said, we are going to use the parallel plate capacitance result, kappa epsilon naught A over D. So parallel plate capacitance to facilitate our derivation here, keeping in mind that our end result will be true for any shaped capacitor, whether it's the parallel plate or not. So our area, as it shows here, cancels out, and we are left with a very convenient, as it shows highlighted here, V squared over D squared. We know voltage equals ED, and there should be constant. There should be an N here for constant E. So E equals V on D. So we see that conceptually the V squared on D gives us electric field, and there we have our final result here at the bottom, that the energy density for the parallel plate is 1/2 kappa epsilon naught electric field value squared, and that is our joules per meter cubed. The most important thing for us is not to be able to go through and memorize this derivation, but to know that the relationship between the electric field and the energy density stored within that capacitor is proportional to E squared. So in other words, if we double the electric field, we quadruple the energy density between the plates of the capacitor. And conceptually, we need to focus also on the fact that the energy itself is stored within the electric field. So pause the page here, get all of these annotations, and we will move on.